Welcome to this presentation on electrophilic addition and elimination. We're basically going to be breaking down these two elementary steps and explaining the mechanism and their significance in organic chemistry. Electrophiles are species that are attracted to the negative charge that comes from electrons. Electrophiles are usually electron deficient or are missing a full octet or have some kind of positive charge. Electrophiles are attracted to areas of high electron density, including lone pairs on atoms and pi bonds, areas where negative charge is being concentrated, basically. Electrophiles act as Lewis acids, as they are wanting to receive a lone pair of electrons, and will receive a lone pair of electrons when able to in a reaction. And some common electrophiles in organic chemistry include the hydronium cation here, hydrogen halides with their polar bond creates a partial positive on the hydrogen that helps it act as a electrophile. Then we have nucleophiles, and a nucleophile is a molecule attracted to the positive charge that comes from protons. Nucleophiles are usually electron-rich or have a full octet or some kind of negative charge on the molecule or atom. Nucleophiles are attracted to areas of low electron density, and really all molecules and ions with an available lone pair or a pi bond have the ability to act as nucleophiles because they have some level of excess electron density, but their actual likelihood of acting as an electrophile changes based on their reactivity. And nucleophiles act as Lewis bases because they have the ability to donate their lone pairs or tend to donate their lone pairs in reactions. And so we have some common nucleophiles include the hydroxide anion, also halide anions with their negative charge, and then organometallic reagents, because when these are dissolved in solution, we see that the positive cation will disperse and will be left with the negative anion. And so now the next important player in electrophilic addition and elimination reactions is going to be alkenes and alkynes. Basically, alkenes and alkynes are hydrocarbon chains that contain one or more carbon-carbon multiple bonds within the structure. We know that alkenes are characterized by 2 bonds between 2 carbon atoms, and that alkynes are characterized by 3 bonds between 2 carbons. These molecules contain pi bonds that exist above and below the plane of the molecule. We can see right here we have area of electron density above the molecule as well as below the molecule. And these areas are areas of high electron density because we have basically 4 to 6 electrons that are being coordinated between the space between 2 atoms. These pi bonds, being weaker than the sigma bonds, can potentially act as a source of electron density for sigma bonding with other molecules. And so we'll see that showing up later in electrophilic addition, that when we have an electrophile approaching this area of electron density here, that this pi bond is going to be weaker than our sigma bond, and it's going to want to basically break off and form a new sigma bond. So electrophilic addition is an elementary step in which pi electrons of a substrate, typically an alkene or alkyne like in this example here, basically attack the electrophile. And this attack results in the breaking of the pi bond and leads to the addition of the electrophile to the substrate and forms a new sigma bond between the carbon atom and the electrophile. So in this example, we have a basic alkene with a double bond, and then we have a hydrogen halide containing bromine. And because of that polar bond between hydrogen and the bromine, we know that the hydrogen has a partial positive charge as a result of bromine's electronegativity as an atom. And so when our electrophile comes close enough to either an alkene or an alkyne with the carbon-carbon pi bond, the electrophile is attracted to the negative charge of the electron-rich region between the two carbons. This attraction is strong enough that the bond between the hydrogen and the bromine is broken, and the bromine is going to go ahead and take the 2 electrons of the covalent bond with it, forming a bromide anion, while the hydrogen bonds with one of the 2 carbons. This step results in the formation of an unstable carbocation and a bromide anion. Because of the formation of an unstable carbocation, electrophilic addition is often going to be a part of multi-step reactions, and really it's going to be very rarely taking place as a single isolated reaction. For example, in this reaction, we would likely see the bromide anion bond to the positively charged carbon here. As a result of the process of electrophilic addition, we see that a pi bond is broken here, and that one of the 2 carbons involved in that pi bond is now bonded to our electrophile here. And the other carbon involved in that bond is now positively charged and relatively unstable in energy, meaning it's going to be very reactive and it's going to want to form a bond basically with anything that it can, and that's why we so often see that it's followed up by another bond with whatever it's available. And so in order to help memorize the curved arrow notation associated with electrophilic addition, we can remember PAP. PAP stands for pi attacks positive, because we see that our pi bond attacks the positively charged electrophile. So if you're needing to remember the steps associated with electrophilic addition, just remember PAP. So we have a couple of examples here. In our first example, we have a relatively simple alkene and then diatomic bromine. And even though the bromine doesn't contain a positive charge in this example, it's still able to act as our electrophile, because when it comes close enough to our pi bond, the pi bond is going to induce a temporary dipole on the diatomic bromine, giving the closer bromine atom a very slight positive charge and giving the further away bromine a very slight negative charge. This causes our pi bond to break and a covalent bond to form between one of our carbons and the bromine atom, while the bond between the bromines is also broken. And this leaves us with a bromine substituted alkane and a negatively charged bromide ion. In our second example, we see that we have an alkyne and then a hydrogen halide containing chlorine. And just like our previous example, one of the pi bonds is going to attack the partially positive hydrogen atom, causing the bond between the hydrogen and the chlorine to break and forming a sigma bond between one of the carbons and the hydrogen atoms, leaving us in the end with a positively charged carbocation and a negatively charged chlorine ion. So electrophilic elimination is going to be the reverse reaction of electrophilic addition. It's basically what pairs with electrophilic addition as one of the pairs in the 10 elementary steps. And electrophilic elimination results in the formation of an alkene or alkyne and the removal of the electrophile. So electrophilic elimination is a little bit simpler than electrophilic addition. It really only involves one arrow in the curved arrow notation of the reaction, and that is the redistribution of electrons from the sigma bond here between one of the carbons and the electrophile to the bond between the 2 carbons, creating a pi bond. As a result, we're left with a simple alkene and an excess theoretical proton. So electrophilic elimination is adding a pi bond back to our substrate, while electrophilic addition is going to be taking away a pi bond from the molecule. To help you memorize what's taking place in electrophilic elimination, I have a little mnemonic device. and it's sigma to pi, say goodbye. So in electrophilic elimination, we have electrons moving from a sigma bond to the pi bond, so that's the sigma to pi. And then our electrophile is leaving the substrate. Unfortunately, we're going to have to say goodbye to the electrophile. And so when you think of electrophilic elimination, think sigma to pi, say goodbye, and just by remembering that, you're going to be able to remember the basic steps of what's going on. It's a lot easier than trying to mentally picture the arrow notation taking place and the changing molecular structure. Again, we have a couple of examples here. In our first example, we see that we have a carbon chain here with methyl substituents and a positively charged carbon atom. And the electron density from the sigma bond between the carbon and hydrogen here is moving to form a pi bond between the two carbons here, causing our hydrogen to break off as a proton from the rest of the molecule, resulting in the formation of a more stable alkene in the end. And then in our second example, we have a bromo-substituted alkene with a positively charged carbon. And we can see that the electron density from the covalent bond between the carbon and the bromine is being moved over to form a pi bond between the two carbons, causing our bromine to break off as a positively charged cation. And now, for the vast majority of the time in organic chemistry reactions, bromine is going to be a leaving group, and it's going to be ending up as a negative anion. But just for the sake of this example, we're going to assume that this is one of the few instances in which it's going to form a positively charged ion. So the big question really comes down to, why are we learning this? What's the importance of this information? And so electrophilic addition and elimination shows up pretty much all throughout different organic chemistry reactions, and will be a big part of in understanding reactions in later biochemistry classes, things like that. Being part of the 10 elementary steps means that it plays a pretty integral part in deconstructing different reactions into simpler steps that we can use to understand better what is occurring. An example of a reaction that electrophilic addition plays a part in is the Prinz reaction. It's a form of coupling reaction. You can see here a coupling reaction is just a reaction in which basically two molecules are being bonded together. And so in the Prinz reaction, electrophilic addition of an aldehyde or a ketone to an alkene or an alkyne occurs and results in the formation of multiple possible products depending on the solvent being used and the surrounding temperature and acidity of the solution. But this reaction can form products including triol here and dioxane. Electrophilic addition and elimination also plays a major part in different synthesis reactions, especially like biosynthesis reactions within the body. Electrophilic addition is involved in biological synthesis reactions that basically help to develop and build complex organic molecules that help to make up the structure of our body. For example, in the synthesis of fatty acids, one of the key steps in this multi-step reaction is the electrophilic addition of acetyl coenzyme A units to a growing chain that ends up leading to the formation of a fatty acid chain. And so, yeah, electrophilic addition and elimination are important concepts to understand and master as you progress through organic chemistry and other biochemistry classes. And I hope that this presentation was helpful.